So the plan for the lecture is that I want to finish up kind of the previous lecture, and that's going to take a little while. And then I'll talk about stationary measures as time will permit. So the model that we were ultimately interested in looking at is this colored stochastic six-vertex model. We saw it has a limit to the colored ASAP, and we saw a whole story about that. While I have this slide up, let me just kind of point out two things. So the first, this is the result of starting under this special kind of rainbow initial data, linearly increasing orders, analogous to the packed initial data for colored ASAP. And the analog of the height function that you should have in mind is that if I look at some later, say, vertical direction, so I think of maybe time in the horizontal, and I look at some height, I can ask how many particles are there of a given, of color bigger than or equal to something that sits beneath that point. So I could just count up the number of colored arrows, and I can put a cutoff on where I kind of count. I only count colored arrows that are higher than color 70 or 80 or 90, right? And so in this way, I can define a colored height function. So if I look at a given slice, for each choice of cutoff, and then for each height that I'm at in this picture, I keep track of the number of arrows beneath me. Okay, so that's going to be the analog, as we saw in ASAP, of this HTX, or HXYT type object, the thing that was measuring the cutoff for having a given step initial data at position X, and then you're measuring the height function at time Y. The other thing I want to mention is that this model has nice projection properties. So, again, let's imagine I'm taking this special type of a packed initial data, or rainbow initial data. If I project all numbers between 1 and 3, and I just call those 1, 2, 3 as a certain color, and then I project colors 2 and 4 to a single color, and then I can maybe project everything above it, what I'll get is a system with fewer colors. Okay, so in other words, as long as the colors are somehow clustered in a sequential way, and you project the system, you end up with another colored system with just fewer colors. Okay, and this is just because the only interaction that matters is kind of whether the relative orders of colors. So as long as you preserve under these projections relative orders, you're perfectly good. So in particular, if I'm interested, let's say, in knowing just like the joint distribution of the height function for everything of color bigger than or equal to 1 and everything of color bigger than or equal to 10, I can just project everything between 1 and 10 and call that some number in between. And then everything bigger, I'll call it 10, and everything smaller, I'll call it 0. And I'll end up with a system with only 3 colors. Okay? So depending on how many kind of slices of this height function you want, you can actually look at a restricted system with fewer colors. Okay, so anyway, so this was the model, and what we determined, well, first of all, we talked about the Yang-Baxter equation. Recall, this is a statement that says that if I look at this 3-term partition, or 3-vertex partition function, and I sum out over all the internal ways of rooting the external arrow assignment. So I have all these external arrows. I can have an arbitrary assignment of colors, let's say 0 through n. Then the partition function here, which will depend on the spectral parameters x and y through taking ratios when you cross a vertex. So the x partition, the x spectral variable kind of follows the horizontal path, and the y follows the horizontal path. And then you could even imagine a z spectral variable here. And you always take the ratio of the kind of horizontal to vertical spectral parameter when you're determining what the weights are. And Yang-Baxter says that for any choice of these external facing arrows, the 2 partition functions on the left and the right are the same. Okay. Now, we then spoke briefly about the notion of fusion. I didn't give you a proof of this, but what I explained was that through this process whereby you kind of take a Q exchangeable measure on an assignment of arrows incoming and then you sum out over all ways that they can be routed through and kind of keep track only of what the content of the outgoing arrows, but not the location of the outgoing arrows is, you can define what's called fused vertex weight, which keeps track now just of kind of a multi-vector of how many arrows there are of given colors coming in vertically and how many there are coming out horizontally, and still we can have at most, or we can have exactly one color coming in on the left and one color coming out on the right. And as a result of this procedure, you get another solution to Yang-Baxter that involves an intertwining of two vertices that have this L matrix and one that has the original R matrix, the sort of single vertex, 6-vertex partition function. Okay, so then there's some nice applications of this to generalize the 6-vertex model to others. But what I want to describe is what happens. So, you do this fusion procedure, right? You introduce two new parameters in principle. Well, let's say we only do fusion in the horizontal. So you introduce one new parameter, and then you can do some nice analytic continuations. And what you get if you do that, well, you can get an intertwining or a Yang-Baxter equation that relates the 6-vertex weights to something called Q boson weights. In fact, there's a gauge transform, so these are no longer stochastic. But nevertheless, you have the following seemingly more complicated Yang-Baxter equation, which I'll unpack. So here now the vertical directions, because we've done this sort of fusion and analytic continuation, these are bosonic, so they can accommodate an arbitrary number of arrows of arbitrary color. So you can have 50 color 1 arrows and 3 color 2 arrows and 75 color 4 arrows. And depending on the choices of those, so that's this sort of multi-vector A. You don't need to concentrate too much on the weights. You can compute then, still in the horizontal, you can have exactly 1 arrow of color between 0 and n. And you compute a partition function here. How do all of these arrows get kind of routed through? Most of them need to come out on the top because you can only kind of exchange 1 arrow on the horizontal. And you get a relation of this sort. So
sorry, then.
Yeah.
But through this exchange process, the number of particles
there's always conservation.
Total number of particles.
So not only that, there's conservation of the arrows. Okay. So if you have 5 arrows coming in of of color 2, then there will be 5 arrows coming out of color 2. So there is conservation, not just of the number, but of the number of each type. Okay, so what is the point going to be now? So the point is that we have, on the one hand, something that involves these Q boson weights, and then on the other hand here, we still have a 6-vertex weight, because we haven't done any fusion in this vertical direction. And the Q boson weights seem harder. They seem more complicated. They're kind of nasty, and these seem easier. So a priori, it's not clear what we're going to gain by using this. But if you'll bear with me for one slide, I'll tell you. Okay, this is just a picture of, it's inconvenient to need to keep writing all of these summations. So if I draw an equality of pictures, what it really means is that you compute the partition function of both sides with the specified boundary conditions. In other words, you sum out over the internal routing of arrows and the product of the weights, and that these two partition functions are then the same, okay? So this is the... So that's what I mean by this sort of convention. And so with that in mind, here's the argument that relates the colored Q boson model to the colored stochastic 6-vertex model. And the basic premise of this argument is that this is going to play the role of this Feynman trick. Okay? So the Feynman trick, remember, you inserted this exponential factor and you kind of took your interest from t equals 0 to t infinity, and you went from something oscillatory to something localized. So what we're going to insert is not e to the minus tx, but rather we're going to insert in a vertex model whose partition function is 1. So what do I mean by that? So imagine the following. You're interested in studying the stochastic 6-vertex model with a particular set of colors inputs. So sigma 1, sigma 2, sigma 3 are the colors on the boundary. You've kind of rotated the picture 45 degrees. There's nothing coming in from below. And you want to know the probability that the arrows exit in a certain order in certain locations. Okay, this is ultimately the type of thing we care about in this game. Now, I can append to this on the left a vertex model where I have these Q-boson vertices, okay, whatever they are, you don't need to worry too much, and where I put the input arrows coming in on the upper left region, and I have all zeros coming in below. I choose spectral parameters to be 1 up here and z down here. Now, the effect of this is actually completely trivial because in all of these vertex models, arrows can only move either horizontal or up. So if you start all of your arrows kind of on the top, they can't do anything. So I'm going to specify that nothing is exiting in the top, nothing is entering the bottom of the system. And so all the arrows can do is go horizontal. And so the partition function corresponding to this entire picture factorizes into the partition function of the left part of the picture, which is just 1, because the weight of all of these kind of horizontal passing arrows is somehow trivial in this example. And then the partition function here, which is exactly the probability distribution of a particular outgoing state of the stochastic 6-vertex model. So it doesn't look like I've done much here, right? Like I've just multiplied this by 1. Let me just back up for 1 second. When I write this picture, I'm using the same convention from before, which is that I specify the outgoing and incoming arrows. So I assume nothing is coming in from below, and the configuration of what you see coming in leaving on this side, nothing leaves on the top. And all that comes in on the side is arrows of type 0 on the bottom, and then sigma 1, sigma 2, and sigma 3. And so there is a partition function which involves a massive sum over all of the internal ways that everything could get rooted. But what I've just said is that actually there's only one way things can get rooted on this left section. And so that factorizes out. You get a factor 1, and then you get the probability here of the stochastic 6-vertex model. Now, when you're computing that large partition function on this left-hand side, you can compute it by kind of summing out over all rootings except for the rootings in this little pentagon here. Okay, so this little region here, you could kind of leave that for computing it last. And if you think about what that means is you've kind of fixed the boundary vertices of a little Yang-Baxter section, right? Like if you back up, you see this sort of pentagon. Once I've fixed the values on the outside of it, I can move the cross through. So what you're going to do now is, by using Yang-Baxter, you're going to commute this cross, this first cross here, to the left by 1. And then you can continue to move it through. And as you do that, Yang-Baxter says that the partition function does not change values. Okay? So you peel that cross all the way to the left. And then once you've done that, you can peel the next cross all the way to the left, because you're kind of, when you move this through, you're left with a slightly bigger looking Yang-Baxter left-hand side. And you pull that through, and you keep progressively pulling everything. And eventually you pull it all to the left. And Yang-Baxter tells you that your partition function is equal to the right-hand side here, the partition function of the right-hand side. So what have you gained? Well, okay. So I had these ... meant that there are a lot of maybe there's a bunch of these vertical lines. Of course, it means nothing over here because this is trivial. But when you put the ... in here, what will happen is, so there's, these lines that enter in, they don't actually need to go straight through. They could kind of weave their way up. They just need to exit in the right locations. The problem is that as the number of these Q-boson columns goes to infinity, if ever you have a path that enters from the left into this Q-boson in the upper region of the Q-boson space, you have this spectral parameter z here, and if you consult these vertices, the weights of the vertices, anything that has a horizontal path gets a factor of the spectral parameter. So if I assume that the spectral parameter z is strictly less than 1, and if I have a path that is rooted into this region on the top, as the ... goes to infinity, the weight will diverge like z to the infinity. So in fact, it will diverge to 0. So the contribution to the partition function, which is a sum over all rootings of paths of the product of all the weights, will be 0 from any path that enters it. Now, of course, there might be lots of ways of doing that, so you need to kind of balance the two. But what you ultimately show is that as the number of columns goes to infinity, the only paths that contribute to the partition function are those that are rooted down into this bottom section and then stay there infinite, for almost all of the duration, and then only in the last finitely many steps make their way up to the right. Okay? So that tells you something. That tells you now that this becomes a trivial weight. It's actually no longer 1, but it's some simple product of these types of factors. And then you have the kind of weight of the consideration of kind of infinite, paths coming in from infinity on this bottom section that eventually need to wind their way and make their way up into here, but only do so kind of in the last finitely many sections. So what have we done is we've related now the height function of the stochastic 6-vertex colored stochastic 6-vertex model to somehow a different model, a different vertex model, which is this colored Q-boson model, in particular the last column of the colored Q-boson model. So let me just kind of summarize this picture on the left here. So let's say that I had only 2 colors, color 1 and color 2. I inserted 2 colors 1 and 2 colors 2. And so I want to know, so I can define a probability measure on all of the paths that route from this boundary to, in fact, I can, with no additional cost, I can force them all to exit at the top. And if I look at the marginal distribution of this probability measure, so this is a probability measure because what I do is I take the product over every vertex of the Q-boson weight, and then I have some normalization by a simple product form. And so if I look at the last column of this, and I look at where do these arrows cross, this is by virtue of this Yang-Baxter proof, this is exactly equivalent to the marginal distribution of where the arrows exit in the colored stochastic 6-vertex model. Okay, so somehow this Q-boson model embeds the height function in its last column of the colored stochastic 6-vertex model. Now, at this point, it's good to pause and say, what have we gained here, right? What we've done is we've taken a very, I would say, simple model, this colored stochastic 6-vertex model, and we've embedded its height function in an arguably more complicated model, which is this colored Q-boson model. Okay. Now, what we've gained, however, is that in the colored stochastic 6-vertex model, the behavior in the bulk of the system, so if you kind of change one vertex, rather than an arrow going straight through, you have the arrow kind of weave to the right. The effect of that on the height function is very minimal. Okay, so you need lots of those things to happen to change the height function in some considerable manner. Okay. Now, of course, since you're dealing with vertex models, you have Gibbs properties, right? If you fix all of the weights outside of some region, that what's inside is somehow determined by the boundary and the product of the weights. But that's not going to be so useful because the bulk has so much contribution. Now, it will turn out, as I'll explain, that in this colored Q-boson model, you actually get a sort of trivialization of the model in the bulk. You can kind of see this, right? The things kind of need to trivialize as you go deeper into the system. And all of the interesting fluctuations and phenomena occurs around the boundary of the system. So there's going to be a way to interpret this in such a way as to extract the scaling limit of just the behavior at the boundary, which is going to give us our theorem. So in order to do this, I want to describe to you 2 Gibbs properties that this colored Q-boson model enjoys and how they lead us to the asymptotics. Okay? So to do this, let me first introduce another way of parameterizing. So this is the routing of these colored arrows. You could also keep track of a height function for this. So for instance, in the first column, I can keep track of how many arrows there are of any color above me. So there will be 4 arrows initially, and then eventually it will drop down to 3. It'll stay 3. It will drop down to 2, It'll drop down to 1, and it'll be 0. So this purple picture here keeps track, so the L sub 1 keeps track of how many arrows there are above you in the first column, and then L sub 2 keeps track of how many arrows there are above you in the second column of any color, and L sub 3 how many are there above you in the third column. And eventually, of course, this will trivialize to kind of be whatever the initial data was that was specified all the way in the boundary. So it would just linearly decrease and then be 0. The L super 2 line ensemble here keeps track of how many color 2 or larger arrows there are, again measuring it in the first column, the second column, the third column, and so on and so forth. So this is just another way of parameterization of this. And you see the thing that we actually care about is only the first column. Right? The first column ended up being related to 6 vertex. And so we want to know what the scaling limit is of this top curve, L11, and the top curve of the color 2 ensemble, L21. And how do we extract that is going to be the question. Okay, if we can do that, then we will have extracted the scaling limit of at least the 2-color version of the stochastic 6-vertex model. You know, we should imagine taking the number of colors here to be large. You know, each one of these is growing in some manner, and that's what we're going to study. Okay, so there are 2 Gibbs properties coming from this Q-boson model that will be very useful for us. So the first one is what we'll call the intercolor Gibbs property. And if you recall, and I don't expect that you do, but in the context of this sort of directed last passage percolation model, there was this Nomi-Yamada identity. There was an identity that related a variational problem for kind of an arbitrary starting point to a variational problem in the push forward under RSK. And this intercolor Gibbs property is going to play a somewhat similar role. So what turns out to be the case is that if you're given the information of the uncolored Gibbsian, the uncolored ensemble, in other words, just keeping track of how many arrows there are, you can actually recover the information about the second type 2 or higher line ensemble through a variational formula. Or at least, so when Q equals 0, you recover, for instance, if I want to know the law of the kth curve of the type 2 ensemble, I can recover it from the knowledge of the kth curve of the type 1 and then the k plus first curve of type 2 through something called a Pitman transform. This is some sort of transformation that often occurs in this sort of area. And then when Q is not equal to 0, this is not an exact variational formula. You don't have an identity that recovers, but you have some sort of probabilistic bound that says that I can kind of guess pretty well what the second curve, you know, what the behavior of that kth curve of the type 2 ensemble is going to be by doing the Pitman transform, and the error on that guess is somehow super exponentially decaying. Now the point here is that let's say when Q equals 0, this basically tells me, I can iterate this, I'll write it down in a moment, but it basically tells me that if I care about the top curve of the second ensemble, I can write it in terms of the entire first ensemble through some sort of iterated Pitman transform, because I can kind of keep representing the k plus first curve in terms of the k plus second curve, in terms of the k plus third, and I can just iterate this process. And this is basically saying that when Q is not equal to 0, I don't have much error around that sort of iteration. So the point of this identity or approximate identity is that it reduces the consideration of the colored model to essentially the consideration of the uncolored model and some variational problem. This is some sort of variational problem in it. So if I iterate that variational problem, this Pitman transform, in fact, I get something very similar to what we saw in the context of this last passage percolation, which is you get this sort of Lax-Olenek or Hopf-Lax type expression, which says that the jth curve of the type 2 ensemble can be expressed in terms of some much lower curve plus the maximum over all paths that kind of connect those two times and levels moving through the L1 ensemble. So the point of all of this is to say that if I care about the colored ensemble, I can recover it in some approximate way from the uncolored ensemble through a variational problem. And that's good because this airy sheet was defined through a variational problem in the airy line ensemble. And so what we really are left to do, besides using this, is to make sense of what happens to this uncolored line ensemble, in particular to relate it to the airy line ensemble. And so that's where, if you look at the uncolored model, it also enjoys a Gibbs property, just again from the fact that this Q boson model is defined in terms of a product of a bunch of vertices, and this is what the Gibbs property is for that. So when Q equals 0 in this Q boson model, Q being this quantum parameter, and you're looking at the levels of this Q boson model, here I've again looked at the line ensemble interpretation of it. The law of, say, the second curve condition on the first and the third curve is simply that of a Brownian, or sorry, of a Bernoulli bridge, and that goes either down by 1 or just horizontal, conditioned to not cross the curve above or below. Okay, so it's just the uniform distribution over all Bernoulli bridges. So that's a very nice object. It's pretty easy to see that that's some sort of discrete version of Dyson-Brownian motion, right? Like here you have non-crossing Bernoulli bridges, here you have non-intersecting Brownian motions. And so it's very reasonable then that you might have a scaling limit of such a system converging to the same thing as the scaling limit of the Dyson-Brownian motion in some large n limit. And that in fact happens, okay? And that can be shown through determinantal methods because this is, non-intersecting paths. You have things like Lingstrom, Gessel, Viennot, you have determinantal formulas for such things. What happens when Q is, so that actually covers like the sort of TASAP case, the Q equals 0 case. But when Q is positive, the Gibbs property is actually a little weird, okay? And this creates all sorts of issues that one needs to address. So when Q is positive, what happens is you still have the weighting according to non-crossing Bernoulli bridges, but then every time that the distance between two consecutive paths in this ensemble decreases by 1, so here you see it was equal to 1 and now it's equal to 0, and here you see this distance was 2 and then it goes down to 1. Every time you have such a decrease, you get a factor of 1 minus Q to the value before the decrease. So in particular, here you would get a factor of 1 minus Q, and here you'd get a factor of 1 minus Q squared. And so that changes the nature of the Gibbs measure. Now, if you imagine that these paths are somehow separating, right, and we kind of expect that they'll separate on the scale of n to the 1/3, if n is our scaling parameter, then this 1 minus Q to some large number is basically just 1. And so as long as you can kind of show that the curves have separated sufficiently, it's not going to really impact the scaling limit. You can kind of hope or guess that you'll still see the airy line ensemble arising here. The problem is that this 1 minus Q factor actually has the effect of trying to coalesce paths. So there's kind of two competing features. You have a non-intersecting or a non-crossing condition, but then as the paths get closer to each other, they actually get some sort of benefit. So you need to worry about the effect of this. Like, can you get yourself into the right frame in which you don't have a coalescing of paths, or the paths don't try to stay close together. And that ultimately is a challenge, but one that can be achieved. And so the way that you basically proceed is in the following way. So you first show that as the number of or the size of the system goes to infinity, you show that you have, for the top part of this line ensemble, you have a GeV Tracy-Widom fluctuation, and you have this Hall-Littlewood-Gibbs property, or this Q boson-Gibbs property I was just describing. Then you need to show that somehow at the edge of the ensemble, things behave in the correct scale. And this takes quite a lot of work for the reason I was just explaining. And you show that any subsequential limit then has this Brownian-Gibbs property. And finally, you use this strong characterization result of Agarwal and Huang to identify the limit as the airy line ensemble. In the course of kind of showing that you have the correct scalings, you need to contend with the fact that the inclusion of this 1 minus q factors kills something called the FKG inequality, or the monotonicity. But I won't go into this, but this is kind of the technical guts of it. OK, so just to put it all together, the goal was, and then I think I'm going to move to the next part of the lecture. So the goal was that we wanted to study the fluctuations of this kind of height field for ASAP, or equivalently for stochastic 6 vertex. And you may as well first study it at 2 or 3 or k. For any finite dimensional distributions, you can kind of look at a few slices. So here I'm looking at 2 slices where I fix x and say x1 and x2. And then by this projection property, I can reduce my consideration, say, to a 2-color system, with colors 0, 1, and 2. So then we had this through Yang-Baxter. We related this to a pair of line ensembles, one which was the uncolored line ensemble determined by this Q boson weights, and then the colored one where we only keep track of colors too. And the analog of the information of the height function along these 2 slices is the top curve of both of these 2 ensembles. We just argued that given the Gibbs property for this uncolored ensemble, we can extract a scaling limit to the area line ensemble. And this is simply by virtue of knowing that there's a 1-point fluctuation that is GUE, and then kind of establishing that that implies that the entire ensemble in this sort of KPZ scaling is tight. It has kind of subsequential limits, and then using a uniqueness result to identify that all subsequential limits need to be this object, the area line ensemble of non-intersecting Brownian motions. Then this approximate variational formula that came from the intercolor Gibbs property tells us that, in fact, jointly, the top curve, or in fact, top curves of the colored ensemble need to converge to something that can be defined through a variational problem in terms of this first object, this area line ensemble. So the limit of the picture on the right is actually defined in terms of variational problems of this object on the left. And if you put that all together, that's the definition of the area sheet. Okay? So that is essentially the punchline of how it all fits. And of course, if you want to look now at multiple slices, 3 slices, 4 slices, you kind of iterate this process. You get a representation that kind of keeps bringing you back to variational problems in this area line ensemble. Okay, so let me kind of summarize, or maybe mention a few directions first and then summarize. So I gave you this sort of picture when we do fusion of many other models that can be related by Yang-Baxter. And the approach that I've described actually applies to all of them. Okay? As you do it, there's some work to be done. You have variants of the Gibbs property. You have more complicated versions of this Q boson model where you have not just one arrow horizontal, but potentially many arrows. Another challenge is to study models with boundaries. And in fact, I'll talk a little bit about that in just a moment when I talk about stationary measures. But we're working on extending these techniques to try to extract the kind of full space-time scaling limits of models in the presence of boundaries. And then there's kind of all sorts of other results. There are interesting mixing time results about models, or fluctuations of second-class particles, or large deviation. All of these things one can approach from the perspective of these kind of colored line ensembles and Gibbs properties. And then, and in fact, also one can attack questions about stationary measures, as I'll explain in a moment. Okay, so this just the summary of what we did. We looked at the full KPZ scaling limit of ASAP, colored ASAP, and 6 vertex. And of course, there's many other consequences of that. We spoke about a few, but there are several other corollaries. We went to a fuller mathematical object, which was kind of this embedding in terms of the Q boson model. And then by virtue of the Gibbs property that one gets from that, we were able to extract the scaling limit. Okay, so I think this is a good time to pause for any questions about this, and then I'm going to transition to something different and arguably simpler. So, any questions? Okay.
I was wondering, this Yang-Baxter equation, is there an interpretation in terms of soliton crossing? Because it seems that on the one hand, I mean, you do something, then you look at the reversing, or is it?
Yeah,
is it
so
related?
no, it's related. It's related to scattering theory of. To give an exact relation to solitons in integrable systems, I need to think a little bit more to how to say it. But yes, there are, for instance, there are limits of these vertex models which become box ball systems, and box ball systems are these sort of ultra discrete versions of KDV and TOTA. And I think that from that perspective, you can kind of see the soliton behaviors in terms of Yang-Baxter. But I shouldn't say too much. Okay, I'm going to transition to the board now. Okay. Okay. All right. Let's wake up. So I'm going to describe something different now, and very self-contained. Can we get a little more light, or can people see? That's it. Okay. Fine. Okay. So I'm going to be interested in the remainder of this lecture about stationary measures for the KPZ equation. So this is the stochastic PDE that goes by the name of the KPZ equation. Okay, you should think of h as a height function, so it depends on time, and then x, so it takes values in the reals. Time is bigger than or equal to 0, and x takes values. Well, there's some choice where x takes values. Okay, so you could consider x taking values in the reals, and we'll call this the sort of full line case. You could have x taking values in something like a torus, right? That would be called a periodic type model. There's actually interesting stuff in the periodic model. You don't actually need h to be periodic. You just need the sort of monodromy of h. You could have a model where you have h kind of wraps around like that, and then you kind of imagine that you just kind of replicate that periodically. Okay? So you don't actually need to have a slope 0 for periodic KPZ. Or you can have like a half line, or you can have an interval, say 0, 1. And sometimes this is called the open KPZ, okay, or finite. Now, each one of these, of course, has different values, different interests. And generally, the open one is considered the most complicated one to deal with, because you have the effects of boundary. So let me describe to you what I mean by open and what are the boundary conditions here. And I'll say, in my notes, I also talk about the periodic one, which is very interesting, but I'm not going to do that here. So for the open KPZ, maybe I'll do it down here. For open KPZ, you also need to specify boundary conditions. And the boundary conditions that you take are at the boundary 0s and 1. So if you evaluate this at 0, or if you evaluate it at 1, you should get some given slope is the claim. So here you have two parameters, say u, and you have v. And for some conventions, we want it to have a minus v. So what this means pictorially is the following. So imagine that you start with some sort of interface. You don't even actually need the interface to start with the right slopes at 0 and 1, because this PDE, so what the PDE is doing is it's smoothing you out, right, locally. Yep.
Since we already a-dimensionalized space by fixing the coefficients to 1, does it make a difference if you change the length of the interval?
Yeah, good question. It does. So in fact, you should do 0L. The effect of L is pretty minimal on formulas, so I'm just going to take it to be 1. But it is a legitimate parameter that needs to be considered. But I'm not going to remember how to do it, so I'll just leave it as 1. Okay. Good question. So what was being said is that you have parameters here, and usually in the full line case, you can kind of change your way between parameters by just doing scalings of time and space and then the height, because that gives you kind of enough ways to perturb it. But if you have a fixed interval, you can't do that, right? Like you lose one of the freedoms. So there's actually a one-parameter family of KPZ equations on 0L, indexed by L. And then actually for each given L, there's a two-parameter family indexed by U and V. So U and V, what they're basically doing is they're enforcing certain slopes at the boundary. So if you look at this after some later time, maybe here you'll locally have slope U, and here you'll locally have slope minus V. Okay, and of course here you have a smoothing term, here you have a lateral growth term. This kind of wants you to spread out. And then this is space-time white noise. Okay. Now, I should say, and I know this is not primarily a mathematics audience, but making sense of this equation mathematically is hard because the thing is very rough, right? So of course, making sense of this with a non-differentiable function is hard, but also making sense of the boundary conditions, right? The thing looks locally Brownian, and so what does it mean for the derivative of something locally Brownian to be U? Well, okay, there you can kind of say it looks locally like a Brownian with drift U, and that's more or less correct. But there is the way that you really make sense of this is that you exponentiate and you have a stochastic heat equation with certain Robin, mixed boundary conditions, and then that's a well-defined object, and you basically take the limit of that, or take the logarithm of that. Okay, so just before stating a result, let me say why might you care about this object? Of course, if you're interested in interface growth in the presence of boundaries, where somehow the interaction with the boundary, imagine there's certain substrates here that kind of enforce certain slopes, right? And this happens, for instance, in sand piles, right? There's like certain slopes that can be established, or if there's certain interactions with different materials that kind of lead to certain slopes. The other reason is that if you take the derivative, so if you say, call U the spatial derivative of H, then U actually solves something called the stochastic Burger's equation. And this boundary condition is just an enforcing that you have a reservoir of a certain density U and a certain density minus U, minus V. Okay, what does it mean to have a negative density? Forgive me, it doesn't exactly make sense in that language, but it's essentially, what is being said is that this is essentially, when you take the derivatives, it's essentially the same in notion as something like the open boundary ASEP, where you have certain rates at which particles enter in and certain rates at which they exit. And then, jumps occur inside with certain rates. So the derivative is kind of a similar object to this open ASEP, if you've ever encountered this object. And the values of U and V have to do with the values of these boundary rates. Okay, so let me state a result. Let me first state a definition. So for this KPZ equation, you can ask about stationary measures. And the thing which is a little tricky about this is that, you start it off and it's going to run and it will kind of just keep doing something. And there's absolutely no reason, there's nothing that pins down the actual height. So there's absolutely no reason why the height won't just kind of diverge to infinity in some direction over time, right? Like just keep drifting away. So when you talk about stationary measures, you need to actually talk about stationary measures either for the derivative or for kind of increments, some centered version of this. And this is, again, also the case, you can talk about the stationary measure for open ASAP, and that's fine because that's at the level of derivatives. But if you look at a height function, a sort of cumulative current of the system, then it doesn't have a stationary probability measure. So let me say an initial data H naught, I'll call it, I always go back and forth between stationary and invariant, but they mean the same thing. I'll say invariant, I guess. If the law, so I look at the law of the solution to the open KPZ equation for x in 0, 1, is t independent. Okay, so if I start with an initial data such that if I, not deterministic, right? It shouldn't be deterministic. But if I start with a random initial data, which after any amount of time, if I just close my eyes and then look at it, I say, oh, well, that has the same distribution on that initial data, modulo centering by the value at 0. So I kind of need to look relative to this value. Then I call the measure invariant. Okay, is that fair? It's really the same notion as you would have in a particle system.
This is the law as a process?
As a process in X, yeah. So the entire process, And so, of course, the question is, what is, first of all, are there invariant measures? And what are they? Okay. So in the context of something like the full line, the invariant measures are pretty simple. The invariant measures are again, maybe I'll pin it to be 0 at 0. The invariant measures are two-sided Brownian motions. In other words, I choose a slope, and then I just take a Brownian motion of that slope in the positive direction and minus that slope in the negative one. Okay? And that will be invariant. And that's analogous to the fact that for something like exclusion processes, Bernoulli product measure on the full line is invariant. In a periodic setting, it's similarly relatively simple that the single, if I look at a given slope, so I kind of imagine I have a torus. If I look at like a Brownian bridge of a given slope, that Brownian bridge will be invariant on the periodic model. Okay? There's interesting stuff when you ask what happens if I kind of take two different slopes and run the system coupled by the same noise, and what's the joint law of all of that. And I talk about that in the notes, but I'm not going to do that now. The presence of the boundaries in the half space, the half line, and the open considerably change the structure of the stationary measures. And so here's the result. So let me kind of continue the definition and define something. So I'm gonna give you the stationary measures in a moment. So let's let B from 0, 1. Okay, I can literally write L everywhere, so let me just do that. Okay. If I remember right, it doesn't matter. To R, be a Brownian motion of, and for some conventions, I'm going to choose the variance to be 1/2. I could have chosen different coefficients and had Brownian motions of variance 1. But what I mean by that is that if I look at a unit time and I look at the interval, the increment of the Brownian motion is a Gaussian of variance 1/2. So it's just some scaling of the diffusion coefficient. Okay, and let Y also from 0L to R be independent of that Brownian motion with Radon Nicodem. I'll tell you what this means in a moment. Derivative with respect to a free Brownian motion of variance 1/2 proportional to the following. Okay, so I need to unpack this in a moment. What I'm writing here has a name. It's a boundary, one-dimensional boundary Liouville quantum gravity measure. Okay, so what is a free Brownian motion? What I mean by that is I take Lebesgue measure on the y-axis, so it's not a probability measure. Okay? And then at a point chosen according to Lebesgue measure, I just put in a Brownian motion of variance 1/2. Okay? And then, well, okay, run to time L, run to width L. Okay? Now, there's a claim now, so maybe we'll start with a theorem. So if u plus v strictly bigger than 0, then we can. Sorry, bigger than, strictly bigger than 0. Then we can renormalize. So y is y has a probability measure. Okay, what I mean by that is, again, a priori, I'm starting with something. Let me just give you an easier way to think about this. Imagine that I have Lebesgue measure. That's not a probability measure. But I multiply it by a density. Let's say the Gaussian density, e to the minus x squared over 2. And divide by square root of 2 pi. So I've taken something that's an infinite measure. I multiply it by something. That something now creates a finite integral. And I can renormalize by whatever the value of that finite integral is to get a probability measure which had that density, that specified density against Lebesgue. Okay? That's like the usual way you construct a continuous probability density. So here what we're doing is we're taking an infinite measure, which is Lebesgue cross Brownian, and we're reweighting it according to some density. Now the claim that's first being made is that if I choose u and v to be the sum to be strictly positive, then if I integrate over that infinite measure, this density, I get something finite. So in other words, I can divide by that finite partition function, and I get a probability measure that is kind of over all paths with their starting points. It's no longer going to be, it's some sort of tilting of this type of object. Okay? So why is this true? Let me explain just very briefly. If you imagine, let's say, imagine an even simpler case where u and v are both strictly positive. What's going on in this Radon-Nikodym derivative is that it gets really, really big when u is positive, when u0 or ul are positive. So there's some sort of forces in terms of the energy that that wants you to go up, right? Yep.
Yeah, sorry if this is a bit of a rudimentary question. I've come across the Radon-Nikodym derivative, but I've not used it. Do you have a quick and dirty?
It's just that it's the density. So when you're defining like a continuous probability distribution against Lebesgue measure on the line, it's just the density function. And now you're dealing with a more general, more general measure space. It's just the density function. So literally, if I'm going to compute any expectation of a function under this measure with this Radon-Nikodym derivative, I just insert this factor in, compute my integrals with that factor in. Okay. But you can also think of it just as a sort of an energetic reweighting. So the way I want to think about it is I sample under this infinite measure, I sample somehow a path, I propose the path, and I say, well, how does this treat the path? Does it like it? And so it's going to like paths that start high and end high. Let me assume u and v are both bigger than 0. It likes things that start high and end high, but it also likes things that go low in between. Because you see, if you're high here, you have e to that, and then you have a minus sign. So being high in the middle penalizes you actually exponentially in terms of the energy, and being low in the sides penalizes you linearly in terms of the energy. So what this basically means is you have some sort of confinement, right? Like, you don't want to be too low here, and you don't want to be too high here. Yep.
But you said that we're looking at measures on Lebesgue cross Brownian.
Yeah.
But this is why it's only a function of space.
And a starting point. So Lebesgue is the starting height. So I'm thinking of y, let's say y of s, and then y of 0 is distributed according to Lebesgue. And then y of s minus y of 0 is distributed according to Brownian motion. Yeah. So anyway, the result of this is that because of this, you have confinement. Your paths, basically your paths want to go high and then quickly go low, but Brownian motion penalizes you for doing such things. And so because of that, the integral, this normalization is finite. You can actually compute the normalization explicitly using some knowledge about the n equals 2 quantum tota Hamiltonian and things of that sort, but we don't need any of that. So that's the argument when u and v are both positive. In fact, when u plus v is positive, in one case you kind of might align, but there's such a penalty from the other side, right? You might have something like you still want to go low here, but the penalty of starting low here is too much, and so there's some sort of balancing act. So it's non-trivial that it all works. But here's the theorem that I want to get to, which is that if I now look at my first Brownian motion of variance 1/2 plus the increment of my second reweighted object, this Liouville quantum gravity type object, and I look at this as a process in X. So this is an invariant measure. Is that what they called it? Or this is invariant. This is invariant for KPZ. Maybe I'll call it LUV. Okay. So in other words, once I've specified L and I specified the boundary condition, this is an invariant measure for it. So the Brownian motion plus this independent kind of reweighted object. And in fact, obviously I need to kind of center by the value at 0, because at 0, the invariant measure should be 0, right? So this is 0 at 0, and this difference is 0 at x equals 0. And in fact, moreover, it is unique. Okay, so not only is it unique, in fact, you can prove convergence to it from any initial data in exponential time. Yeah.
Yeah. So in practice, how do you implement the boundary conditions? Should it be clear that if you take it's possible to create an ensemble of curves such that the subtracting off the deterministic part both satisfies the boundary conditions and has the right correlators?
So you're asking, let's say you wanted to numerically simulate the evolution of this equation, how would you kind of do it in a stable way at the boundary?
Both that and whether it should be clear that there is truly an ensemble of curves that satisfies the boundary condition and such that the stochastic part has the right correlators.
So I don't know if I understood the second part of the question, but you know, to the question of how to make sense of the equation and the boundary conditions, you know, it's not trivial. So for instance, if you wanted to go to some discrete model and you want to get it to converge to this, there are corrections that one needs to implement at the boundary depending on how you're doing it. You know, so you could work, for instance, directly with a model like this open ASAP, and I have a result with Hao-Shen that shows convergence under weak asymmetry of this model to the open KPZ equation. You know, the other way to simulate it would be that you do this Hopf-Kohl transform, so you write, you know, z is e to the h, and that transforms these boundary conditions into certain mixed boundary conditions for the relating derivative of z to z at the boundary. And then you can write down a sort of iterated, you know, there's what's called a chaos series. So you can kind of iterate the Duhamel formula for this stochastic heat equation with boundary conditions and get an expression kind of in terms of multiple integrals with respect to space-time white noise, which, you know, you can solve, you know, you can compute, you can do all of that. So that would give you another way to actually numerically implement these things. I don't know if that answered all of the question, but we can talk afterwards also. Okay, so I want to explain to you where this result comes from or how to think about it. And then I also want to give you, you know, there's something slightly unfulfilling, which is that, you know, you need u plus v to be bigger than 0. Okay, so first let me kind of put this result into context of, you know, where it came from. So, and maybe I won't write everything on the board, but, you know, the story starts a while ago. So it started, in some sense, well, at the introduction of asymmetric simple exclusion process. You know, Liggett, for instance, studied this model in the 70s and did study some structure of its stationary measures. But the kind of innovation really came in 1994 in this work of Derrida, Evans, Hakim, and Pasquier on the matrix product ansatz for ASAP. So this was a way of writing down the stationary measures in terms of some infinite dimensional objects that satisfy certain commutation relations. If I have time, I'll say something about it, but I think I have something in the notes about it as well. Solving the matrix product ansatz, you know, getting expressions for the stationary measure that somehow look nice in the spirit of what we're seeing here is hard, and a development there of importance was the work of Uchiyama, Sasamoto, and Adati from 2003. They related the stationary measures for open ASAP to some things called Askew-Wilson polynomials and the sort of Jacobi matrices for those. And then finally, there is more recent work of Brick and Wisłowski relating this model to something called Askew-Wilson processes, and then my work with Kniesel, which proves this, taking asymptotics of those objects. And the thing that's weird along that initial route towards this theorem was that nowhere along the way did you see the beautiful structure of, you know, I consider the answer to be a pretty object, but nowhere along the way do you see that pretty object emerging. There are other ways to see it, and there's, for instance, some representation of Derrida and Eno that has a little bit more of a flavor for this for ASAP, but this was not the original approach that was taken. So what I want to do, if I have, I'll probably have time, I want to say something about where you can anticipate this sort of structure from a discrete model. And I won't focus on this, the ASAP, but I'll focus on a related model. The other thing that I wanted to say just before I get to that is, what about this restriction? Okay, what happens if u plus v is not equal to 0, or it's not bigger than 0? Okay, so in fact, you know, what happens when u plus v equals 0? It turns out when u plus v equals 0, the stationary measure simplifies considerably. It just becomes a Brownian motion, a single Brownian motion with slope u, or, you know, minus v, whatever, whichever one you want. But that's not at all apparent from this, right? The whole balancing act kind of goes away in that limit. And so there was a conjecture, which is now proved, that if you look at this measure, so you can see. So this was an argument due to Barraquand and Ledoussal. So if you look at this, you see the only thing that this depends on is the difference of y of 0 minus y of x. And so what you ought to do is you ought to rewrite the Radon-Nikodym derivative. If I call that, let me call this thing y tilde of x, right? Kind of this centered object, y tilde. Then we see that the thing that matters is b of x plus y tilde of x. And the thing that doesn't matter is y of 0. Right? Somehow the y of 0 value is of separate interest. So I can rewrite the Radon-Nikodym derivative as the following. So there's some dependence on y of 0. And then dependence on y of s. Put this in. Okay. This is just a change of variables of this formula here. And so because y of 0 is distributed according to Lebesgue measure initially, and I only care about y tilde of s, I can now integrate out over y0. I integrate out over the 0 mode. And that integral can actually be computed. So if you have, this is just a real, a calculus problem. So if I kind of match this, so you should think of A as being, this is like what I'm calling, this is what I'm calling A. This is what I'm calling X. This is the same as e to the 2x, and then this is what I call B. So anyway, I can compute this integral, and it's 1/2 b to the minus a gamma of a. And so if I do that, I can show that y tilde has a Radon-Nikodym derivative against a variance 1/2 Brownian motion with a sort of drift minus v. This creates a drift for my Brownian motion, which is given by this expression. So the point is that I can integrate out the 0 mode. And after I integrate out the 0 mode, I get an expression for the thing that actually matters, right? It's b of x plus y tilde of x. And this Radon-Nikodym derivative now makes sense actually for any value of u and v. And in particular, if u and v, if the sum is 0, then this Radon-Nikodym derivative is just 0. Or sorry, it's just 1. It's just something to the 0. It's just 1. And so then y tilde becomes a variance, a half Brownian motion with drift. I think it's actually drift 2v. 2v, and if you add that to an independent variance, a half Brownian motion, you just get a Brownian motion with drift. Drift v, which is what I claimed when u plus v of 0 is to be the stationary measure. But this makes sense for even u plus v negative. And so the conjecture was that this is the stationary measure for any u and v. Proving that directly is hard, right? Because whereas this measure makes sense for any uv now, one doesn't necessarily know how that, the stationary, these invariant measures somehow continue, right? Like you could have an object whose formula continues to some other set of parameters, but for which that no longer is physically meaningful for that. It's not an unreasonable thing to hope that it's true, but it also doesn't mean that it's true. So what you might want to do is you might want to prove something like that the stationary measures for, or invariant measures for open KPZ depend analytically on u and v. in some sense, right? And then you do some sort of analytic continuation argument. But that seems hard, right? Like, first of all, these are infinite dimensional objects. They're measures on curves. And what does it mean for such an object to depend analytically on U and V? So what we didn't know how to do was directly prove that this is the stationary measure. So what we did instead was we showed that we can find a structure for some discrete models that takes the same form, but for the discrete models, one can actually implement an analytic continuation argument. You can do an analog of this integrating out trick, and then you can take a scaling limit of what you get as a consequence, and that will give you proof of this. So this is, in fact, a theorem that this holds for all U and V. You don't need any, and as long as you use this expression here. Okay. So I have a few minutes left, and maybe what I'll do in those few minutes is tell you one model. It's a discrete model of last passage percolation for which this sort of structure that we see for KPZ is replicated at the discrete level, and which kind of indicates why this is the stationary measure. I haven't proved to you, I haven't explained to you at all why, in what sense or why this is the stationary measure, right? Like you might want to just check, hit it by the generator of the stationary open KPZ and check that you get 0 or something like that. Doing that directly seems hard, but doing that at the level of the discrete model turns out to be pretty manageable.
Sorry, the relation with Lewis gravity is just a fun fact?
Just a fun fact. To some extent. It's a robust fact, right? Like it's something that holds because, so these stationary measures can also be seen as coming out of these vertex models. And the vertex models, so the fact that you get in the bulk this sort of Liouville measure is just by virtue of the fact that this is related to the Hamiltonian of quantum tota. Okay, so this is this exponential Hamiltonian, it's Laplacian plus exponential interaction. And so, if that, whether or not that is a fun fact or not is up to your discretion. The boundary conditions come from the boundary solutions to Yang-Baxter. So, all of this ultimately is coming from Yang-Baxter. So I guess it's somehow, I don't know exactly what would define a fun fact versus something not in this case. It's certainly not two-dimensional quantum gravity, right? So that's, one should be clear about, right? This is a one-dimensional version. Okay. So let me describe to you a model which is called geometric Actually, let me go back to the slides now, because otherwise there's going to be too much drawing. And we can, let's see. Let's see if I can do this right. Ah, okay, perfect, okay. So you can read anything that I didn't cover. Okay, here's the model. This is, we imagine that we have a strip of Z2, okay, so some sort of diagonal strip. And we specify some set of numbers on the bottom, G0, 1, or G0, 0, G0, 1, up to G0, n. N is the width of the strip. And I specify G0, 0 to be 0. The model is going to depend on 3 parameters, A, CL, and CR. And I'll assume that their product of the A's with itself and then A with the C's are all between 0 and 1. And I do that because I want to define geometric random variables with those parameters. So now I define what are called weights, Wij. So the weight on the left boundary is going to be a geometric with parameter A times CL. In the bulk, it's going to be a geometric with parameter A squared, and the right, it's geometric with ACR. Okay, so just a bunch of independent geometric random variables I've populated in this strip. Okay. So now I define a recursion, which is called the last passage percolation recursion, which is just that I say that, okay, GNM is equal to the weight at that location plus, well, if I'm on the left boundary, plus the weight of plus the value of G right beneath me. So if I was here, I take the value immediately beneath me. And if I'm on the right boundary, I take the value immediately to the left. And if I'm in the bulk, I take the max of the two values to the left and below. Okay. If I take this recursion and I iterate it, and of course I need to specify some initial data, and the initial data is this G naught on the bottom. If I iterate this recursion, you see it basically gives me the maximal path through these weights, starting off at wherever I am, say Mn, making my way back to the bottom, and then kind of sampling this initial data. Okay, so this is really like a hop-flax type thing. You know, it's a variational object. You could just as well change plus and max to multiplication and addition, and this would define a directed polymer model. Okay? And in fact, there's a similar analysis to what I'll describe here for a model in which you have this positive temperature, this directed polymer, where the geometric is replaced by something called an inverse gamma weights. In any case, we call an initial data G naught. You know, you think of this G naught as like the KPZ initial data, and this is the evolution is like the KPZ equation. It's the thing that propagates it forward. And so in the same way, we call G naught an invariant measure if the law of the increment process. So if I look at height, say, n, and I look at n plus k n minus nn. So in other words, I look at the difference of the values along this horizontal of G minus the value at the left point. If that is a stationary, or if the law is independent of what the height shift k is, then I say that G naught was an invariant measure. Okay. So really the increments of this G are like the occupation variables, for instance, in ASEP. And okay, I gotta do it this way. And I want to give you the stationary. So you know there are invariant measures. This is relatively easy to prove, and I want to tell you what they are. And you'll see that they have a somewhat similar description to what we saw for the KPZ equation. This is not a. This kind of explains the origins in some sense. So the description I give is in terms of something called a two-layer Gibbs measure. There is also a way to relate this to a matrix product ansatz, but I should say for this model, the matrix product ansatz doesn't just involve two matrices. It involves two infinite families of matrices that need to commute in some very complicated ways. So solving that directly seems hard. But OK, so the structure of the invariant measure is the following. So in fact, rather than looking at the stationary measure only on a horizontal, I can look at it on any downright path. So if I specify an initial data on any downright path that connects the two endpoints, I can still propagate that by the recursion. And it's pretty clear what it means to be invariant. That again, that the values minus the value at the left boundary should not depend on how you've shifted the system upwards. So I define something called a two-layer Gibbs measure. What I do is I take the downright path. So maybe I'm interested in just the horizontal, or here I kind of have a path that goes down, right, down. And I rotate that and I duplicate it. So here's the sort of down, right, down, and then I draw the same picture beneath it. So I have two layers. And then I connect it on the left by this little circle and the right by this little circle. And this defines something I'll call a two-layer graph. So that's just a graph I associated to the path gamma. And then a configuration on the path is that at every vertex of this path, a configuration on the graph is that at every vertex, I put some natural numbers, or some integer numbers. So I label all of the vertices x0, x1, x2 up to xn, and then y0 up to yn. Okay. Now I define a Gibbs measure, which is currently an infinite measure, on the configuration space by taking the product over all edges. So this graph has three types of edges. It has the curved edges at the boundary. It has the edges between, within a layer, and the edges between layers, these dotted edges. And what I do is, given a configuration xy, I take the product of the weight of all edges, where the weight of the edges are as follows. So the weight of the, that's not good. Oh, there we're back. Where the, I think I pushed too hard and the whole screen became. I need to ease up on this thing. Do you think? Does it grow as I push? No. Anyway, so the weight of connecting x to y is just this boundary parameter CL times x minus y. And the same thing on the right-hand side, CR times xy. These are like these boundary weights, this e to the u times, well, whatever was written here, the analog. And then in the bulk, you have, within layers, you have that if you had a y followed by an x, or an x followed by a y in the downward direction, you get a factor of a to the y, x minus y times an indicator function that x is bigger than y. And then the dotted things just don't have this a factor. So this defines some measure. And I say it's an infinite measure because everything depends on the difference of x and y's. So if I added 1,000,000 to everything, it doesn't change the weight. Okay, so there's a sort of overall invariance with respect to shifting everything. So what the theorem says is that it provided the CL times CR is less than 1, and you should think of this as the analogous to u plus v being bigger than 0. There's a relation. If I restrict my measure on this two-layer measure to paths that start off so that x0 of 0, x of 0 is equal to 0, then the measure is normalizable, much in the spirit of what I was describing for this Braudo-Nikodym derivative. You can normalize it to be a probability measure on this collection of x's and y's with, again, x of 0 equals 0. And if you look at the marginal distribution of the top level, the top layer, it is, in fact, the unique ergodic invariant measure for geometric last passage percolation with these parameters. So the message here is that if I want to, if I looked at this recursion, this geometric last passage recursion relation on the line, I could also define a recursion on the full line. And there is a nice invariant measure there. It's just some simple product form for the increments. This is analogous to the fact that ASEP has Bernoulli as its product invariant measure. When I go and I introduce these boundary conditions, I don't have a product form anymore, but I have something that's kind of almost as close as you could hope. Right? The measure that I'm looking at here, so product form would be that I just have a one-layer Gibbs measure. Right? If I have a measure which just has a single graph and the interactions are just between neighbors of the form of products of weights, that's a product measure. So all I do is I insert in an additional layer, and I take that measure and I look at the marginal on the top, and that gives me the invariant measure. Okay? So that's the theorem. And in fact, one can also do the integrating out trick that I was describing here and release the condition on C and L to be less than 1. And I probably won't go through that. But what I want to do maybe in the last 4 minutes is tell you why is this the invariant measure, or at least give you some sense of how you prove it. And it's actually a relatively simple proof. The idea is the following. You have, here I've defined a measure given a path gamma. Okay? There's no reason for you to believe me that this is the invariant measure. Okay? But let me postulate that it is. So what I'd like to do is I'd like to say, well, if I start with this measure, in other words, this marginal of the top curve of this picture, I'd like to say that if I kind of grow a box, if I invert this and it goes horizontal and then down, I'd like to show that what I get is still a measure of this form. It won't be the same measure, but it will have the same kind of top layer of the two-layer Gibbs measure. And if I repeat that, eventually I'll get back to the original thing that I was interested in. So that would give me a proof, a sort of a local checking that adding, using the recursion locally preserves the class of measures. Okay, so that would be great. Proving that directly is actually slightly tricky, but what you can do is actually prove that there is a dynamic not on just the normal LPP, but a dynamic acting on two-layer graph configurations whose projection to the top is LPP and whose invariant measure is exactly this two-layer Gibbs measure. So you actually, again, embed this in a higher dimensional object. So rather than just looking at the LPP recursion, you look at a slightly more complicated recursion. Let me skip through this. Well, okay, there's a little bit to be said, and I probably won't say everything, but the basic premise is that you are looking for finding a way to find if you start with the measure, I'll call mu gamma. This is the measure on the path on the two-layer graph given by gamma. You'd like to find a transition matrix, a probability that maps you to the gamma prime, where gamma prime is the result of having kind of either grown a bulk edge, or, added a box in the bulk, or added a triangle at the boundary. And a priori, finding such things is not simple, but there are some nice identities that are pretty easy to check, things called Cauchy and Littlewood identities, that allow you to construct exactly such dynamics. And ultimately, what you show is that you can construct dynamics that kind of do a local update. So if you have local configuration with some values that are specified here, the probability that you go to another local, where you've added in a box, or here you've kind of added in a corner, you can identify what the conditions are for that preservation to occur, and this becomes some sort of local conservation or preservation of weights. So this identity, this is the bulk identity, there's a similar one at the boundary, you can look for solutions to this identity, and you can look for, there are various ways to do it. One is to somehow forget where you were, and this actually immediately gives you a dynamic that has the Markovian projection to last passage percolation. So this is the premise of it. So essentially, you've constructed a dynamic on these two-layer configurations which preserve local weights in such a way as to preserve the measures, and which project, when you look at the top layer, to last passage percolation. And so it follows immediately from that the stationary measure of the projection is the projection of the stationary measure. And there's just a bit of left to check that the normalization constant is finite. The integrating out step is quite simple. It's basically this gamma integral that I wrote down before. It gets replaced by just a geometric sum, and you can sum out the zero mode, which is equivalent to x of 0 minus y of 0, and it gives you an expression which is similar in flavor to the one that I wrote in terms of this general u and v. And now you can use some simple complex analysis to prove that the stationarity is actually, the stationary, or these invariant measures are analytic in these two parameters, CL and CR. And this allows you to extend to prove that, in fact, for all values of boundary parameters, this is the stationary measure. OK, so maybe I'll just flash for your own purposes, in case you're interested in matrix product ansatz, that this is a version of matrix product ansatz. Right, so matrix product ansatz, here's a way of rewriting the measure that I wrote down, which is that the probability measure given a path gamma is some pairing of some vectors and matrices. And these matrices depend on, so x, in ASAP, x's are like the occupation the increments of x are like occupation variables. Here, the increments of x are not just 0 or 1. They can take arbitrary natural number values. So for every choice of that natural number index, I have a different matrix. So I call this MD. And whether or not my path was a horizontal path in gamma or a vertical one, I have a different matrix too. And so I get some representation just by matrix multiplication of the formula for these two-layer Gibbs measures in terms of a matrix product ansatz expression. And these infinite matrices are not complicated. Their matrix entries are somehow relatively simple. They're not tridiagonal or anything of that sort either. And you can show that this is a solution to a matrix product ansatz. And in fact, you can check that you can write down what that matrix product ansatz looks like, and it looks complicated. So for those who know matrix product ansatz, usually it involves two matrices for ASAP, D and E, and they satisfy some quadratic commutation relation. Here you have two sets of infinite matrices MD over and MD down. And these need to satisfy these infinite commutation relations. Even guessing that this model would have such a structure seems a little bit tricky to begin with. And then solving this seems a little bit tricky to begin with. So our approach doesn't go through matrix product ansatz. I didn't go into where our formulas came from, but they do come from the structure of these vertex models that I was speaking about in the previous lecture. One can kind of use that to infer the nature of these invariant measures. OK, so I'm going to wrap it up here. Just to give you kind of a review. So in the first lecture, we spoke about these random walk and random environment models. And it was very much the kind of physical picture. I gave you a bit of a flavor of the stochastic analysis that relates and allows us to compute things. That model is a special case of the vertex models that I talked about in the second lecture. I focused there on the stochastic 6-vertex and ASAP and developed the machinery that allows you to extract the full space-time scaling limit. One of the things that you get out of that by kind of looking locally at these pictures of these line ensembles and understanding the effects of boundaries, which I didn't go into, actually ends up relating to these stationary measures. So everything is ultimately connected in ways that are not entirely clear through the lectures. But hopefully, if you look a little bit more at the lecture notes, you'll get more flavor, or you'll come up to me and I can explain more to you. OK, thank you very much.
Very much, Ivan. Are there any questions?
Yeah.
So about the general model or framework you told us, could you comment on the relation to the KPZ fixed point? Because KPZ fixed point is also something that controls, in principle, all models in the KPZ class. So do your Vartex model and relating thing and the KPZ fixed point somehow overlap, or what is the relationship?
Yeah, OK. So let me just tell people so the KPZ fixed point, so in the previous lecture, I spoke about this notion of taking some initial data, say H for, let's say, ASAP, OK? And then applying some renormalization operation, right, where I zoom out in time by epsilon inverse, and in space by epsilon to the minus 2/3, and then I scale down by multiplying the height by epsilon to the 1/3. Okay. Now, if H under this renormalization renormalizes to something I'll call, say, curly H, so for instance, a Brownian motion, there's no time for the initial data, right? So it's just diffusive scaling. So Brownian motion, random walk type initial data would converge to Brownian motion. Then what Questel, Remennik, and Matetsky showed was that in the case of Q equals 0, so this was for TASAP, they showed that if you have an initial data that converges to something, let's say something deterministic, they were able to write down a formula for the probability that, well, first of all, what they were able to show was that then there's the sort of ASAP evolution to HT, and they showed that this converges to some process, which is called the KPZ fixed point, some Markov process, who can be defined by its transition probability. So the probability that the KPZ fixed point at time t, say x, is less than or equal to some g of x, given, for all x, given the h0 value. They gave some formulas, some complicated Fredholm determinant type formulas. Okay, but that it characterized it, and from kind of some general nonsense, you were able to prove that that implies a Markov process. Okay, so it's a Markov process, which means that for each initial data, you have an evolution. Okay. Now that was proved for Q equals 0. Okay. Now the theorem that I gave, the second theorem in my second talk, showed something much stronger, in fact. So what it showed was that if I have, let's say, a collection of initial, well, it showed that if I look simultaneously over all initial data and even all times, that I can represent the renormalized limit of the evolution. So maybe what I called it hs at time s. So this is like the initial data at time s, and then I'm looking at position y at time t. So this is the effect of running that initial data, or the pre-limiting version, through this acept field of Poisson arrows, started at time s, run to time t, looked at position y. That entire process over all initial data and over all times, and for all y and for all t, is equal to the sup over hsx plus this directed landscape object. And that this is true for all q. So in particular, for q equals 0, it is also true. And so for q equals 0, we know separately that this is related to this transition probability formulas of the KPZ fixed point. So that implies that, for free in a sense, that if I look at a single hs and a single time s, then the Markov process that I get marginally is the KPZ fixed point. But in fact, they're all coupled together by virtue of them being defined in terms of this common directed landscape, this common noise, the analog of these Poisson arrows that couples them together. So maybe the sort of take-home message here is that if you can, so people worked hard and proved formulas, lots of complicated formulas. We don't need to do any of that because we show that it's the same object. Right? So it's kind of like in usual probability. For Bernoulli random variables, you can write down lots of formulas, and then sometimes you can just show that lots of stuff looks the same as what lots of Bernoullis look like. And so that gives you like a central limit theorem where one is, Bernoullis go to Gaussian, and then everything looks like Bernoullis, right? So one can just do a direct, at the level of objects, probabilistic objects, a direct matching, and then you get anything you want out of that.
Great. Thank you very much.
Are there any questions? Maybe I have also one, because so if you look at the same image at the level of the data, you have this phase transition. And so I was wondering whether there's very specific structure of the boundary layer depending on the signs of u plus v and blah blah. Do you see it in your?
Yeah, exactly. So I didn't write anything about this, but if you look at any of the models, so you look at this last passage percolation, or you look at open KPZ, you also have a phase diagram, maybe if I can do over here. So if I plot u and v, there's a region here which plays the role of the maximal current regime, and there's a region here which, okay, I forget which one is high density and low density, but what does it mean? Okay, I can give it names, but what it means is that if I look at the open KPZ equation with, so that u and v, and I look at the long time limit of the height at, say, the origin, the difference between it at time 0 and time t, then depending on the values of u and v, in the maximal current regime, it will kind of saturate to a certain value, and in the higher or the low densities, it will saturate to a different value. Here, it will depend on u. Here, it will depend on v, and here it will not depend on either of them. So you can prove stuff of that sort. You can also prove results that say that if you look at the L to infinity limit, and you look at the nature of the stationary measures, it will depend kind of in a particular way on this phase diagram. In the last passage percolation model, I think you can do the same. I don't think all of the details have been written down about that, but you can proceed somewhere.
Well, thank you very much. So if there are no more questions, then thanks again, Ivan, for this